Greetings everyone. In previous class we have discussed the mathematical expression of change in resistance with respect to time, and there we got something like this. Change in resistance equals to R naught times alpha delta T, where R naught is your initial resistance, alpha is your thermal coefficient of the resistance, and delta T is your change in temperature. We should be knowing that whether we take change in temperature in Celsius or Kelvin, the change in magnitude is same, right? So it is not the important that you take it in Celsius or Kelvin. It is fine, you can take in any point. Now we are going to talk about a very small topic, that is alpha for different materials. Alpha for different materials. What we will be discussing alpha for different material, we can say very small elaborated expression we have here is that if we are discussing four conductors, then you can, if you remember the theory about conductors, that if you have one conductor at T1 temperature and you have the same conductor at T2 temperature, here initial resistance is R0 and final resistance is, we can say it RF, and if we increase the temperature, means we provide some heat, means here delta T is coming out to be positive, right? What we are discussing alpha for different material, here what actually I mean is sign of alphas. So delta T is positive, we know, and we've also found what? That change in resistance is also positive, means resistance has also increased. So what is the expression we got? The expression we have is delta R naught alpha delta T. See, if I am saying that this term is positive, this term is positive, and R naught resistance cannot be negative, so this is already positive, so alpha has to be positive. You might think like it is very obvious, and it is obvious also, right? What we are interpreting, that for conductors alpha is coming out to be positive. You might think that why we are discussing the signs of alpha, because it is important once we are talking about the semiconductors. So for conductors, this is what we have evaluated. Now we will talk about semiconductors, right? If we talk about four semiconductors, so what you will find for semiconductor here is that if you take a sample of semiconductor, if you remember that if you have a sample of semiconductor, let's say it is R0, initial temperature is T1, here temperature is T2, final resistance is RF. So if you remember, what happens when you heat the semiconductor? If you remember, what happens when you increase the temperature, you give the heat, you get more free electron in your conduction band. That means your conductivity increases. If your conductivity is increased, that means your resistance decreases, right? Why it happens? Because if you increase the temperature, number of free electron density increases for semiconductor. The same thing happens for this also, conductor also, but the difference is for semiconductor that free electron density is already very, very small compared to metals. So any change in free electron density creates significant difference. So that's why, so here what you will see that on increasing temperature, even though we are increasing the temperature, so the change in temperature must be positive, the resistance is coming out to be coming out to be negative. What does it interpret? It interprets that your final resistance is less than your initial resistance. Now if you look at the equation, what equation we had is delta R equals to what? Alpha R naught times delta T. And here you can see this term is coming out to be negative this time, even though when we have taken this term as to be positive. This cannot be negative, this must be positive. So the only thing which can be negative here is your alpha, and it is very important that you write that alpha is negative for semiconductor. Yes, the alpha is negative for semiconductor, only then the mathematical expression can work. So sometimes they ask the signs of alpha, from that you can distinguish metal for conductors, semiconductor and alloys. Now if we talk about alloy, you can take screenshot for this, okay. Then if we talk about semiconductor we have already talked about. If we talk about alloys, what happens if you remember? What happens if you remember that if you have an alloy, and if let's say it is that the initial resistances are not, final resistances RF, and temperature is T1 and temperature is T2, if you increase the temperature by some amount, right, if you provide some heat, remember what we are assuming, that change in temperature is not that big. So if the change in temperature is positive, but remember the change is not very high. So in that case, when the change is not very high, what we found here, that the change in resistance was nearly zero. Nearly zero means that final resistance was nearly same as initial resistance. So what it is implying, that sometimes you can write it equals to, but actually it is, you can always remember, even though I am writing it approximately equal, here RF is slightly more than R naught, but the difference is very small, so we can neglect it. That is the purpose of alloy. What is the purpose of alloy? If you remember the previous classes, you want to have a device, or you want to have a conductor for which the change in resistance is very small, even the temperature is changing. If you remember, I told you it is used to calibrate devices which can measure accurately resistance, voltage or current sometimes. So if we remember the equation correctly, that was the equation, right? And if this is the equation, and we can see this one was positive, this one was positive, oh, this one was positive also, but it was approximately 0, means little bit over 0, but still it can be taken as 0, and it was positive, right, but non-zero. So this equation, this combined equation, can only come to be 0 when you take this very small, this very small, or this very small. And here we can say that R naught won't be that small, change in temperature is small but not very small, means we are talking about the range of change in temperature around 22 or 20 to 50 somewhat. So you can see delta T is also not very small, so we can take it to 0. So the only thing which can convert this equation near to 0 is alpha. So what we found, that alpha is approximately 0 for alloys. So you can also write alpha for alloys very, very small but positive. This is your nature of alpha for your alloys. Alright, so for conductor it is positive, for semiconductor it is your negative, for alpha it is near to 0 but exactly not 0 but very, very small. Sometime in MCQ or some questions they can ask it. It is very basic and you can remember. But in general, if you remember the previous class, in general we know that alpha is also function of time. So in general, the accurate equation we can write is dr equals to r naught alpha, which is also function of temperature, into delta dt. If you see, this is your differential equation. This equation can work at any time because here alpha is function of temperature, and here you can evaluate. Let's have an example so we can do it. Okay, let's say we have a conductor. Let's say the temperature here is 0 degrees Celsius. Temperature here is 0 degrees Celsius. And here is 25 degrees Celsius. Okay, and let's say the alpha of material, I'm taking example, I'm showing you this, you can do the other one. I will write it 0.005 times t square. Let's say this is your this, and initial, let's say they have taken initial resistance to be 100 ohm, and they are saying if the temperature becomes 25 degree, what is the final resistance at that time. Let's say they are asking this. And now you can see if the alpha is simply a number, you can simply use the previous equation to solve it. But because you can see alpha is also function of temperature, that means we have to use this equation. This equation can work at any point, whether you have alpha constant or variable, it will always work. Because if alpha is constant, everything will come out of integral sign, and then you will integrate just dt, that will give you your delta t. But in this case, we have to use differential equation. What we will write? dr equals to r naught alpha dt. What we need to calculate? Final resistance. We can integrate, integral sign. We are going from r1 to r final, right? And here from T1 temperature to T2. Now you can place your values. This integral will give you your what? R final. That's what we have to calculate. And R initial, that was R naught. And here R naught can be out of integral. Alpha will be also out of integral. Not completely, but the coefficient of t will be out of integral. And you will be left with what? T squared times. Let me just. Okay, fine. We will do with this. T square delta t. We are going from 0 degrees Celsius to 25 degrees Celsius. Right? Then you can simplify this. What was your RF? RF we have to calculate. R naught was 100. Right? And this will be your 0.5. And this integration will give you what? T cube by 3, 0 to 25. So RF will be your what? 0.5. You can take 3 outside, and that will be your what? 25 cube minus 0 cube plus 100. That will be your resistance. And if you evaluate, you will get your answer. Alright? Pretty easy. We can do this question pretty easily. Nothing difficult in that. But similar question I will give you. You can try as a homework. Let's say R initial is 20 ohm. R final is, and T initial is your, okay, 0 degrees Celsius.